This video is the second one in a four-part series sharing an engineering framework for food safety. The video before gives the overall introduction and the big picture of such a framework for understanding food safety. This one in particular goes into building the framework for food microbial safety, and the following video shares a short framework for understanding food chemical safety. Here we get into the first one of the two types of food safety that will present frameworks on, the first one being microbial safety. To build a framework, we want to break down microbial safety or microbial contamination into its fundamental building blocks. What are they? So they can be migration is one, how bacteria migrate, how they attach to a surface, attachment is the other building block, and then growth or inactivation, that's the third part, and finally communication is the fourth one. Now discussing framework for all four of them would be too much in this video, and we are trying to stick to two of them, migration and then we'll talk about also the growth in more detail, and we'll talk a little bit about attachment and not much about communication. Communication has to do with bacteria using chemical signal molecules to communicate with one another. Although bacterial communication is important and can be modeled using reaction kinetics and other mechanistic description, we will not get into communication to keep the video short, but also communication becomes more relevant when the bacteria are at very high cell densities, such as when the food is at the end of the shelf life. Also, to keep the framework focused, we'll only discuss a small amount of attachment. So the framework that can include these migration and growth and these types of processes is our good old transport phenomena framework. So in this framework, this is the transport equation that we have derived in our earlier modules, or most of you are already familiar with. So in this transport equation, this term represents storage, and this term represents flow-like processes, directed motion, and this term represents more random motion or diffusion-like processes, and this one represents generation or growth or inactivation and so on. When we are referring to bacteria, this diffusion-like process can be a Brownian motion. What is Brownian motion? It is an incessant movement of that you can see in the video that shows up on the screen. You can see Brownian motion of tiny fat particles by clicking the video on the screen, and so these random movements can be handled by treating them as diffusion-like. We can think of the Brownian motion as simply due to constant thermal agitation. It's because they have thermal energy, they are not at absolute zero. Another diffusion-like movement can be bacterial motility. So what is motility? It's the random, spontaneous tumbling motion of bacterial cells. Again, an example of bacterial motility can be seen by clicking on the video on the screen. So both the Brownian motion and motility are incorporated as a diffusion-like process in my transport framework. Although these diffusivities are typically much smaller than the molecular diffusion coefficients. Continuing with the transport equation as the framework, we want to talk about two other processes in bacteria that are directed motion, unlike the random motion of diffusion-like processes that we just discussed. So let's look at this piece in the can full of water. If we heat this can without agitating, there's going to be flow patterns set up as shown here. And so the water inside will move depending on which way we are heating and so on. This movement, if there is bacteria in the water, that bacteria would be carried due to this movement. That's a very passive movement. It's not because bacteria is doing something by itself. It's simply being carried as part of a convective transport. So in this passive movement of bacteria simply being carried by the flow, we can include it in the transport equation simply by saying that the velocity of the bacteria is equal to the velocity of the fluid. To repeat something, this equation is for transport of bacteria. In other words, the concentration here is bacterial concentration. So this equation has to do with just the bacteria as a species. So that was passive movement. Another situation that can be considered as a directed movement using the velocity term. So using this guy, the velocity term in the transport equation is the chemotactic movement, where the bacteria moves due to stimuli. So as depicted in a second, I'll show. And so when is this chemotactic process relevant? For example, if we have bacteria on a leaf surface, it can actually get inside the leaf, and that's what is shown here. So because of photosynthesis, there could be sugars formed inside the stomata, and the bacteria will drive toward that, and so that is called that's an example of chemotactic movement. Again, an example of chemotactic movement of bacteria can be seen on the video that shows up on the screen. The passive movement and the chemotactic movement, both of them are included in this flow term, or as the velocity in the transport equation for the bacteria. To put things back together in the context of a bacterial transport equation, or transport equation for bacteria as the species, so we see that bacteria migration can be due to diffusion-like motions, that's due to Brownian motion or motility. They're both kind of random motion that can be treated as diffusion-like. And then there are directed motions that are flow-like. So that could be due to chemotactic movement or simply due to passive movement with the flow, like this one. So let's break down this velocity due to external forces. What external forces are we talking about? So external forces can be forces due to flow. When the bacteria is near a surface, there can be near wall forces, adhesion force, collision force, and so on. And then further breaking down, what is force due to flow? When the bacteria is flowing, it can experience a drag, it can experience a lift, just like any other particle, or it can be buoyancy or pressure gradient, and so on. So if we break down all of these, we see that we can have a mechanistic framework on trying to get either the velocity term for the bacteria or the diffusion term for the bacteria. So all of these processes can be included in the bacterial transport equation, and we can provide a mechanistic description of bacterial transport using the general transport framework where the bacteria is a species. Of course, that needs lots of other details, but this has been done. So the framework really works. Next, we want to talk a little bit about attachment. The transport framework that we just discussed provides how the bacteria would be moving. Now we need additional information that as it's moving, how it's going to attach to the surface. To try to understand bacterial attachment on a surface, let's look at flow over a surface. So we have velocity profiles that are like this, dropping to 0 on the surface. So it's a profile like that. So this is how the velocity will vary. This is like the free stream velocity. And this velocity gradient is what is called the shear rate, and the fluid will experience a shear stress one layer over the other. The shear stress is proportional to the shear rate much of the time. And now we think of the bacteria and the forces on the bacteria as it's in the fluid. By thinking of the forces that the bacteria experiences on, as a particle, we can consider the attachment process of the bacteria mechanistically. The force of attachment depends on several biological factors, of course, notably the bond strength, or the force between the cell surface appendages, like these guys, appendages, and the surface, and then the surface chemistry and the number of appendages and the angle of appendages and so on. So if we try to think of what happens as as shear rate, as I said already, the shear rate is the gradient of the velocity. So as the shear rate increases, what happens to these forces? And these have been studied at length. And so here is a composite of some of the studies, and in a very quick few second introduction. So this probability of attachment is small initially. Why? Because at very low shear stress or very low shear rate, there are catch bonds that are weaker, and the particle would simply roll and not adhere. Okay, so this is the composite picture that I was talking about. So probability of attaching is low at this low shear rate. Now, as shear stress increases, here shear stress increases as the shear rate increases, meaning the velocity gradient increases, or at higher velocities, if it increases suddenly, the probability of adhesion forces, it goes up. So it goes up like that because this catch bond strengths increase. At much higher shear rate, like down here, then it will have trouble. It will have trouble attaching, so the probability of attachment decreases. So this framework shows that the probability of attachment increases with shear rate and then it decreases, and it provides a mechanistic sort of insight into attachment and all the forces that the bacteria as a particle experiences. Now, this framework goes into much more detail than our current framework, and we just don't want to get into all of the details of attachment, which would be a separate topic by itself, but only to say that the attachment can be seen mechanistically in a transport plus reaction framework by considering forces a particle, or in this case that is the bacteria, experiences close to the boundary. And so that provides a mechanistic framework for estimating attachment or understanding attachment. After migration and attachment, we want to talk about how growth or death or inactivation can be included in the framework, the quantitative framework, the physics framework that we are talking about. Now, in the area of quantitative food safety or quantitative microbiology, this growth inactivation area is the most developed. So all I want to do is what is already developed, I want to show how that can be nicely included in the mechanistic framework that we are discussing. In the transport framework for bacteria, that's this one, the transport framework for bacteria, where the bacteria is a species for which we are calculating the concentration, where growth, inactivation, and so on would be incorporated is in the source term, as you must have guessed. Depending on the type of growth or inactivation, this term will vary. So I just want to show two examples of how what this term could look like in a mechanistic framework for bacterial transport. For the first example, we choose first order kinetics, the most common example for growth or inactivation and so on. Now, a comment about these reaction orders and so on. So these are empirical or semi-empirical models, but that is good enough for putting things in a quantitative framework that we are talking about to estimate bacterial concentration at any position or time. So here we have The first order inactivation kinetics. Inactivation kinetics, so it has a negative sign here, and it's a first order equation. Now some of you may be more familiar with the D value, but this D value and the K values are related. They both describe first order kinetics. And next, how this K depends on environmental factors like temperature, moisture, etc. And that, in this case, can be described as an Arrhenius kinetics. Again, some of you may be more familiar with Z value. That is equivalent, or can be equivalent to this Arrhenius kinetics under some conditions. So we have the rate constant K here, and its temperature dependency is given by this K0 and the activation energy. Finally, these parameters like K0 or E can also depend on the bacterial strain or the nutrient source, and that is yet another level of information that we may need. Now, these areas, as I mentioned, are very, very well developed in quantitative microbiology. So there's special terms to describe these types of information. The first one is called a primary model. That just shows how concentration would depend or in the reaction. And the second one is the secondary model that shows how the rate parameter K depends on environmental factors and so on. And the third one is called the tertiary model. Back to the transport equation here. What we just discussed, how would they be incorporated in this transport equation for the bacteria? You notice that they will be part of the source term, and in this case the source term, it's a negative source term because it's an inactivation. So this Ra is going to be equal to, for this first order reaction or pseudo reaction that we just talked about, is equal to minus Kc. So this term will be incorporated instead of the source as the source term, and then the K itself would come from its dependence on temperature, like in an Arrhenius kinetics. So that's how the growth, or in this case inactivation, is going to be incorporated in the framework. Another example of inclusion of microbiological kinetics of growth or inactivation into this microbial physics framework is using this semi-empirical or empirical description known as the Weibull kinetics. So here is an example of inactivation, because as you see we have a negative sign. So this equation here describes the Weibull kinetics, where my S is a ratio of concentration at any time of the bacterial species divided by concentration initially, and this kinetics then describes the inactivation process, where B and N are the inactivation parameters. So if we follow the logic that we did for first order kinetics, then this is the description of kinetics, and it's kind of the primary model. And then these parameters like B or N, they depend on temperature. So this kinetic parameters dependence on temperature is our secondary model in case of Weibull. And the B and N can also depend on the bacterial strain, so that would be my tertiary model. So back to the transport equation, this inactivation in this case can be included in the transport equation as the source term. And so if I rewrite the kinetics equation as Ca over Cai is equal to 10 raised to the power minus Bt to the n, then dCa dt is equal to Cai times d dt of 10 minus Bt to the n. So this can be very messy, and the details can be seen in this work, Halder et al. 2007 Journal of Food Science paper. But the point is that's all just simple algebra, and what that will give is the rate, and that's what gets plugged into as the source term. So here's example of yet another empirical description of the microbiological growth or inactivation that can be nicely included in the transport framework for microbiological safety that includes this term for growth or inactivation. It can be nicely included as the source term. So the framework for the microbiological safety in terms of a transport equation nicely holds. So that concludes discussion of 3 of the 4 building blocks. This last one, the communication one, we're not going to discuss at length. And then attachment is something that has a lot more details, as we mentioned, and that can be part of separate discussion. Then the rest of it, the migration and growth inactivation or related items can be nicely included, thinking of bacteria as a species and using the species transport equation where migration can be part of flow or diffusion and growth inactivation would be part of the source term. So that concludes building a sort of a physics framework of the microbial processes of migration or growth inactivation. So the microbial physics framework that we discussed here needs process information. Why? For example, microbial growth needs temperature. So that temperature or moisture will come from the process physics. So the bacterial physics needs to be combined with process physics, and together they do our safety prediction. And this is our overall framework for safety prediction, that is combining the microbial physics framework and the process physics framework. So we will see now 2 of the simplest examples of what we mean by combining this microbial physics framework with the process physics framework By having those examples, maybe things would be more obvious. So let's look at this first example, and I think of this one as the simplest possible example. It's an example from 100 years ago where we're talking about canning process of a solid food. Being solid food, it's just heat conduction. So here is a can, and the heat conduction process will take place from the surface to the center, and there is no movement inside. Again, I chose this one because this has been studied for more than 100 years, starting with analytical solution for heat conduction. So let's look at how we are combining microbial physics with process physics. So the microbial physics in this case is simply the first order inactivation kinetics. So you can see the first order inactivation kinetics just like I described a few slides ago. And we can think of this first order kinetics as a very special case of our transport equation for bacteria. Why is it a special case? Because in my transport equation for bacteria here, written in cylindrical coordinate, in this transport equation for bacteria, we're saying, well, the Brownian motion or the motility, which would be included in a diffusion-like term, is kind of not very significant. And likewise, any movement, any directed movement of bacteria due to either chemotaxis or passive motion inside are zero. There is no passive motion because it's a solid food, and so things are assumed to not move, and the chemoattraction effect is considered small, so we drop this one as well. And so this framework that we have been saying for bacterial transport can readily incorporate this inactivation kinetics, because your RA is going to be equal to minus K0 e raised to minus E over RT times C. So we plug that in here and we can nicely compute the bacterial concentration. So we have a framework for the bacterial physics. But notice that to do the bacterial physics, you need temperature inside. And as this picture shows, temperature is not the same everywhere, and it changes with time. So we need to describe this temperature properly, and that comes from the process physics. So the process physics in this case is simply heat conduction in cylindrical coordinate, because it's a cylindrical can. So it is the temperature that couple the two physics, this one and this one, to provide the safety information. So this is an example of the physics framework for safety. So this is the safety prediction framework example that combines the physics framework for bacteria, here this one, with the physics framework for the process. Here we consider the second example as we move up in complexity. So here we consider the canning of a liquid food. So if we're heating a liquid food, even without any kind of agitation or movement of the can, if it is just sitting there, as we heat from the sides, the hot liquid inside will rise up next to the wall, would rise up because it's heated and therefore it expands and it gets lighter, and so it rises up. And to satisfy continuity, or you can think of the colder fluid would sink. So this will set up a flow pattern inside whether we want it or not. And this brings additional complications as we are considering this liquid food. Now the bacterial physics in this case is the same as the previous one, which is it's still the first order inactivation. But we have a little bit of a problem. Can I just think of using a temperature at any one location? Can we just use that temperature? Think about it. It is the bacteria that we need to follow. And the bacteria is not staying at the same place. As the fluid is moving, the bacteria is moving with it. So we really need the temperature history of the bacterial particle. And that makes it complicated. So the framework, again, for this microbial physics is that transport equation for bacterial species that I reproduced here. Now, in that transport equation for bacterial species, where C is the bacterial concentration, if we ignore the Brownian motion or the motility of the bacteria, we can safely ignore the diffusion-like term for the bacteria. But the flow term we cannot ignore because bacteria has velocities. It has velocities because it's being passively carried by the fluid. So we have to keep those two terms, and then this term, the source term or the inactivation term, how the bacteria concentration just changes because of temperature, is going to come from this guy, the first order kinetics. So Ra is simply equal to minus K0 e raised to minus E over RT times C. But the situation is complex because we have to keep this velocity term. Now notice two things. To be able to do this computation, for the bacterial, the bacterial concentration as it changes with position and time, or the bacterial species, to be able to do that, I need two things. I need the temperature of that bacterial species as it moves. I also need its velocities. So how do I get that? The temperatures and the velocities. Assuming the bacteria is simply passively carried by the fluid, these temperatures and velocities are same as that of the fluid at that same location, and therefore they will come from the process physics. So here is the equation for heat transfer that gives me temperature, but we also need the equations for fluid flow. So here we have the equations for fluid flow, which happens to be what's called the Navier-Stokes equations. But I want you to see that these two equations will give me the U and V, and then this one will give me temperature, and they plug in here and here, and that's how they couple the two equations. And by coupling the two, I obtain concentration anywhere really inside the container, and therefore I can predict the safety. So this again is another example of the physics framework for safety that combines the physics framework for bacteria and the physics framework for the process. This is the third application example of our framework combining microbial physics with food physics. This one is the most complex example of light-driven bacterial infiltration into a leaf. So on a leaf surface, if we happen to have bacteria, that bacteria can migrate inside the leaf, and once it goes inside the leaf, it's very hard to get rid of it. And so this, in this case, understanding and controlling this safety situation is very important. It has been studied quite comprehensively by the authors here, and that's the work that I'm about to describe. So here, if we look at cross section of a leaf surface with the stomatal opening here, during photosynthesis, when you have outside light, then sugars form here. So now there is high concentration of sugar here, low concentration of sugar outside. So if there is a bacteria outside in the water, then the bacteria would like to migrate toward the high concentration, and this is the process of chemotaxis, and that makes this process quite complex. This complex process, however, can still be studied in the context of the bacterial transport equation, where we can obtain the concentration of bacteria at any time or at any position, treating the bacteria as a species. So the chemotaxis would go in here. The velocities due to chemotaxis would go in here, but it's not just chemotaxis. The bacteria can also have motility. So the motility of the bacteria would go in here. And there is also the rate kinetics. So now it's nice to say that all these things are included in my microbial physics, but it needs more information. So for example, the growth rate would depend on temperature. If temperature is not varying as much, if you say, then at least the chemotactic velocities, that will depend on how the sugar concentration is changing with position, and that will come from the photosynthesis process. So we really need to include the process physics. So the process physics in this case is the photosynthesis process and the sugar transport. These are the photosynthesis in particular is a complex process, but it has been described mechanistically, and so does, of course, sugar transport. So if we include these process physics, all of these, then that will give me how the sugar concentration is changing with position, and that will give me these chemotactic velocities. So this is how the food physics would couple with the microbial physics. And therefore, this is another example of safety prediction by combining microbial with food physics. In this concluding slide, I present the framework that we have been discussing with one little added step, little but important step at the end. It also makes the framework look very, very analogous, because it is so with quality prediction or the physics framework for quality that I have discussed in separate video. So safety framework first starts with microbial physics, or something that describes microbial growth or inactivation. It is then combined with process. Why? Because let's say in this example of a heating process, the temperature at any location would be changing with position and time, and therefore the microbiological kinetics would dictate that the bacterial growth or inactivation would also change with position and time, and so we need to combine these two information. That's the second step, combining microbial physics with process physics. We then process this information further according to our interest from a safety standpoint, where, for example, in case of let's say canning, where we are interested in where is the maximum survival of bacteria, which would be at the coldest point in here. So we find where the minimum death is, or in case of growth, where maybe the maximum growth is. So we need to find these information after we have combined microbiology with process. So I call that extracting critical information after we have integrated process and microbiology. As a final note then, we have a physics-based framework for food safety that combines microbial physics with process physics and extracts the most critical information.